Hi, everybody. So today I was going to talk about purfling, a style of edge treatment instead of binding. So far as I know, I don't know if I'm probably not the only one, but one of very few guitar makers who are using purfling instead of binding. And I think we talked about this a little bit some time ago, but the edge treatment here is a lot like the violin family, where the plate overhangs the sides by a small amount, about maybe 3 millimeters or less, 100 thousandths of an inch or so. And then there's a slot, a precise slot cut a short distance from the outside, into which a series of colored stripes are inlaid. The difference between cutting the purfling slot and cutting the binding recess is that the binding is a rabbet cut. In other words, one side of the cut is open. So the binding is applied from the outside of the guitar. Whereas on the purfling cutting, the slot is defined on both sides, and unlike the binding style cutting, there's no room for error. You either cut the slot in the right place or you don't. When I first started doing this about 20 years ago, I called up all my friends who built violin style instruments and asked them if they had a way of cutting the purfling groove that they loved. And my joke about this is grown men wept. Nobody seemed to be really that excited about cutting this groove, and everybody thought it was daunting and difficult to achieve exactly the result that they wanted. So normally it's done with a handheld tool that holds two knives. It's called a Grammel or purfling cutter, and the two knives define the size of the cut. And then you get in there with little dog leg chisels and chisel out the material in between the cutters, and then keep cutting and cleaning out the bottom until you get it the right depth you want. So a little bit of a pain in the neck, and it's tough to know that you've really cut the same depth everywhere, because there isn't any real guide for that. It's all kind of by gosh and by golly. Let me not put it down. I'm not saying that. It's been going on for 500 years or better, and people make it work. But it's daunting and difficult. And of all the people that I called to ask advice from, only two people seemed completely delighted with the way that they were cutting the purfling. One of them was my friend Jim Ham, who's a brilliant builder of all kinds of things on the west coast of Canada. Jim said, "Oh, well, I just built my own CNC machine to make the basses that I make, and so I just cut the purfling groove on the CNC machine." And I thought, well, that's not what I'm going to do. I don't want to do it that way. I'd like to figure out how to do it by hand, sort of. And the other fellow that said that he liked the way he did it was a brilliant violin maker named Sam Zygmuntovich of Brooklyn. And Sam said, "Well, I learned when I was young, I use a Grammel, and it comes out okay." And I said, "Does it come out perfect?" And he said, "Oh, no, it doesn't." And I said, "Well, how on earth do you deal with that?" And he said that he set the knives on the Grammel closer together than the purfling. And he said, so if I make a mistake by moving the tool wrong and the groove gets a little bit wider, it won't be so wide that the purfling won't fill it up. And if the places where I don't make a mistake, I can just take a scraper and slightly reduce the width of the purfling so that it fits everywhere. And he said, and it gives a little difference in line weight, a subtle difference in the line weight of the purfling as it goes around the violin or viola. And he said, I kind of like that. it looks pleasant to me. So as much as I respect those two builders and love their answers, I decided that I was going to go a different way. I spoke with Jim Ham about this, and he introduced this idea of using two bearings. So it was his counsel that led me to devise and build my own rotary cutting Purfling tool, and I'm going to demonstrate that for you. While it's apart for maintenance, I thought I would just show you how it works and how I put it together. Okay, so we're going to start with the cutter, since that's really the business end of any of these things. And here's the cutter that I prefer to use. I auditioned all the 1/8 inch or 3mm end mills and cutters that I could find, and I didn't like the way any of them worked, and I decided to make my own, which has worked out really well. It's a single flute cutter, as you can see. There's not much to it. This is solid carbide, and I grind them by hand. Let me just show you what it is that happens when these tools are ground. So the first thing is that you grind the bulk of the material off and leave a little tiny sliver of carbide left. And what this does is it gives you a whole lot of rake. So it gives you this big rake angle here, which looks like, I don't know, 25 degrees or so, which is what wood wants. And in particular, when we're working on spruce, big problem with spruce is that it's tough, and it's also kind of bipolar in a micro way, in that it has hard lines and soft lines that are quite different in hardness in some kinds of spruce. So the cutter will be singing along in a nice, easy to cut spring wood part of the material, and then all of a sudden it'll run into a hard line of summer wood. This isn't a particularly good example, and this is kind of pretty well behaved, but some spruce, as you probably know, has big strong lines in it, and those strong lines are not just visually strong, but they're also hard and stringy, and they're difficult to cut. So having this rake angle on the tool is a big help. So obviously this is a right-handed tool, and it's going in this direction. Now we have our rake, but we don't have any clearance on the side, so that means that the tool would just rub and it wouldn't advance into the material. After we create the rake angle, we then go to create some side clearance. And in order to do that, we have to grind more material off here and then have that amount decrease until it gets over here to the edge where it's 0 or near 0 that we're grinding off this edge. So that gives us our radial or side clearance, so that when the tool goes to cut into the wood, there's some material removed which allows the edge of the tool to engage and cut into the material. You need clearance for any tool to cut, and this should be a nice, even, smooth curve that you can create. And you could do this by hand on a diamond wheel. Obviously, you have to be careful. Good news is these things are cheap. If you get it wrong, you just grind it off and try it again. But anyway, not that hard a thing to grind. I do use a machine now to grind this side clearance, but before I had the machine, I just ground them by hand, and it'll make you a better person. Finally, cut number 3 is to angle the end of it so that the longest part of the tool is the cutting edge itself. And so this angle is called end clearance, and that's expressed in degrees from the perpendicular. So this is, I don't know what, 5 degrees or so that I've done on this little part to show you what the end clearance looks like. Not too important. When you plunge it into the material, it'll kind of go in there at a slope. Usually you kind of dive in, slide it into the material and into depth. And then The other comment I'll make about depth is that since all we're going to do is cut, I don't know, 40 to 60 or so thousandths deep into the top and back, we don't want the cutter to be longer than it needs to be to do this cut, or very much longer anyway. So that's a big benefit, is having the length of the cutting edge to be short so that it can't deflect very much. And here's the result in a scrap. It just works great. It's a lovely thing, and as I say, it outperforms, wildly outperforms the cutters that I can purchase. And you could use this same idea to make a cutter of any size. Not a hard thing to do. Just got to give it a try. Okay. So then we need to talk about cutting speed. If we do the math, for woodworking saws and cutters, typically we want 5,000, 5,500 surface feet per minute. 5,000 surface feet per minute is almost exactly 60 miles an hour, right? Because a mile is 5,280 feet. So if you went a mile a minute, you'd be going 60 miles an hour. That's the correct speed for the cutting edge. Now, when you do the math, multiply the diameter of the cutter times pi, divided into 5,000 feet, you get 152,000 RPM. 152,000 RPM is difficult to achieve for a lot of reasons, the most important of which being that bearings after about 20,000 RPM get grumpy and don't live a long time. They need to be special high quality bearings to go much faster than 20,000 RPM. Even modern routers have very, very high tolerance bearings so that they can spin at 30,000 or sometimes a little bit more. Here's an air-driven tool by the Dynabrade company called a pencil grinder, and they say very specifically not to use it as a router, which of course is what we're about to do. I'm not really sure why they're telling not to use it as a router, but they sure made it difficult to use it as a router, because the only part of this silly shape that's cylindrical is from here to here. So I had to make these little crazy adapters on the lathe in order to grab it, so that I have a 3/4 inch diameter shank to hold on to. And let's see if I can line this up. So I drilled these holes in here because I was trying to drive some compressed air through the housing and blow the chips out of the tool. I'll add that this tool at 60,000 RPM works beautifully, really spins well, and has quite a lot of guts considering how small it is. The turbine is up in here in the big end, and it really works quite well. By the way, it requires, and indeed cannot tolerate, any lubrication. So whereas in most air tools you need to put a little bit of oil in the air in order to keep the bearings happy, in this tool they tell you never to introduce any oil into the tool. So they're not lubricated, or lubricated for life, I don't know which. Now we have the cutter, most important part. We have a way to spin the cutter at a meager 60,000 RPM, which is well short of the 152,000 that we would like to get, but that's reality, and that's all I could get at the time that I built this tool 20 years ago. I'm not exactly sure if you can do a lot better now. I did look online the other day, and it seemed like you couldn't. However, maybe you can. Now this is an interesting part. This is the core of my holding fixture for this tool. And the origin of this part is that this was designed to go into a milling machine, quite a large milling machine, with a 2-inch diameter shank. And this was originally, well, at least twice as long for this to go into a gigantic holder on a big milling machine. And then this is the collet nut. And of course you can see the collet is this part. And it's captive in there with a, you can see I cut away here to help get the motor as far down as I could, and I exposed this beautiful detail where it has tapered roller bearings in here that take the axial load, so that when you put it together you can easily clamp it very, very forcefully. Of course, we're taking a tiny little cut, not a great big cut, so it doesn't really matter that much, but I mean, we don't need that, but there it is. Okay, so here's, this then becomes the base for the tool. Then the parts that I made to complete the tool include this aluminum ring, which these 3 bolts are attach it to the arm, which we'll see later. But this ring goes on here, and get it on straight. Okay, so that just sticks on there. And then the next thing that happens is this part is, this is a left-hand thread which screws into this, and this was originally designed as a stop for the tool in the holder anyway, but this has been very useful because it helps me adjust the length of the cutting, the depth of cut, that is. So anyway, there it is, adjusting the depth of cut. More on that later. And then here is a ring that I made that goes on and helps us adjust this depth of cut. So now you see when you turn this ring, that changes the height of this part off the tool. Okay, so that's a depth adjustment. And then the next part that goes on is this beautiful bearing. So this is a bearing which lightly presses on. There we go. Okay. That's a light press fit. It's all it needs to be to just hold it in place. I can't get it off easily without prying it. It's just exactly the right fit. Of course, it's wonderful to have a lathe to do all of this stuff. This is the next component, and this is designed to clamp. This clamps onto the bearing, which of course is concentric with the cutter. And you can clearly see that there's a ring in here that's off center. So that's a cam adjustment. And what it does is it adjusts this other little bearing, and this is the follower bearing that touches the edge of the plate. It adjusts the distance of this follower bearing to the center of the tool where the cutter is. So by loosening these 2 screws a little bit, you can rotate this eccentric part, which changes the distance between the edge of the plate and the center of the cutter. Okay, so that goes on here, we hope. All right, then this is the part that actually touches the guitar and creates a floor for the depth of cut. And this is entertainingly made out of 3 pieces of material. I guess I first made it just out of Delrin. This is black Delrin acetyl plastic, but it wore out, so I had to make this stainless end here to go in. So this has to go in first. And this again is a light press fit. Okay. And yeah, this goes on. Okay, I guess that's it. Now, if you look carefully on this side of the tool, you can see that there are lines that I scribed here, and these lines are 10 thousandths apart in terms of the distance between the follower and the cutter. So you can see they change because it's a cam, they get farther and farther apart. So out here 10 looks like this, and then in here it's only a short distance. Anyway, that's how it works. And we can relate this gauge to this line here, which is how we read, that's how we read the position. So anyway, there's the gizmo. And then here's the cutter and the turbine. Push into the collet. So I'll tighten this. And ultimately we end up using this shop-made wrench to give it a good tighten. And we can see now that the cutter is sticking out, and we can turn this and it changes the depth. So there's less cut and more cut. Less cut. More cut. So that's pretty much the name of the game with this thing. This replaced a kind of a odd Grammel that I made, oh gosh, 1979, I guess. I made this. So this was designed to cut the defining edge of the purfling with this little double knife in there, and then to cut away the small shaving every time you used it. And anyway, it worked. Oh, there it sort of works. It was harrowing to use. As I said, grown men wept. And then finally, you got this entertaining little clamp here. So this is a way to restrain this knurled ring from moving while you're using it. So just a hold down there. All right. So that's the gizmo. Next, I'll show it to you mounted on the arm that it needs to hold the tool perpendicular to the guitar while it's being used. Here we are at the rest of the gizmo, and what we've done is bolted this aluminum grabber ring on here with 3 bolts. Well, those are screwed into this piece of 1/4-inch steel, or 3/8, I don't know what it is, 5mm steel. And then you can see that we've got a articulated parallelogram arrangement here so that this always stays vertical. And we've got a hinge here and a hinge over here so that we can get all the way around the guitar. All right, so let's see, in order to, I just kind of quickly put this back together, but I see that the motor isn't all the way down, so we're going to push this in a little bit. Okay. So we're verifying that this is spinning around freely, and have a look at the depth here. I don't know if you can really see this. Hopefully you saw it in the other view. Okay, we're ready to take a test cut here. So here's what 60,000 RPM sounds like. And there's a really, really beautiful cut. Okay. I'm going to rush it a little bit, but there it is. This is just to figure out what our depth is. Make sure we get that right. Just about. And width of this is pretty hard to measure, but it's typically the cutters come out a few thousand smaller than the stock. So this is measuring about 120-ish. Oops. Yeah, about 120, which is pretty typical since the piece of carbide started out right at 125, and it's hard to do that side clearance thing and not nick it a little bit. I don't really care what size the cutter is because the purfling that I'm using is wider than the cutter, so I have to set it over and make two cuts of different distances from the edge. Anyhow, here it is, back in action, ready to run. Thanks for watching.